In this fifth lecture, I'm going to look at a second example of, is this, can you hear me? Okay. At a second example of a polymer with disorder. And it's again going to be something that involves an interface, but the way the interface plays a role is quite differently from what we've discussed last time. And in fact, in the second part of the talk, I will be talking about an interesting random interface. So there's interesting stuff coming up. What we're going to do is the following situation. We're going to look at a copolymer. And as I explained in the first lecture, a copolymer is a polymer that consists not of one type of monomer that you concatenate, but of different types of monomers, two or more. And in this talk, we will be looking at a copolymer that consists of two types of monomers. And the way such a thing is grown is that depends, either it's an object that is there in nature. For instance, DNA is a copolymer with binary disorder. But you can also grow this thing in the laboratory, and you can build these things basically, well, more or less as you please. And what we're going to do in this lecture is consider a copolymer that consists of a random concatenation of two types of monomers, monomers that are hydrophobic and monomers that are hydrophilic. So monomers that do not like to be in water and monomers that do like to be in water. And there will be some, so they will be organized in a random manner. And then what we're going to do is to place this copolymer in the vicinity of an oil-water interface. And then what will happen is that the hydrophobic monomers like to be in the oil, but they do not like to be in the water. And the hydrophilic monomers have exactly the opposite behavior. So here is a picture that I drew of a polymer chain. And along this polymer chain is you see the different types of monomers occurring in some sort of random order. And this random order is frozen in. You cannot sort of, once the order is determined, it would require really a chemical process to change the order, but the order is fixed. And with the yellow monomers, I mean a monomer that is hydrophobic. And a blue monomer is a monomer that is hydrophilic. And now I imagine that I have an oil-water interface. Oil and water do not mix, so I can have a layer of water here, and on top I can have a layer of oil. And if I place this polymer in the vicinity of this interface, then what this polymer might try to do is to wiggle around the interface and try to, each time there is a hydrophobic monomer coming up, to try and move above the interface, and each time a hydrophilic monomer is coming up, to move below the interface. And if it manages to do that, it will get a low energy because it would place all its monomers in its preferred medium. However, it will not be able to do that perfectly because sometimes there will be many hydrophobic monomers coming up, and this part of the polymer would like to be above, but there will be also occasionally hydrophilic monomers coming up, and they, well, since the polymer is attached, they cannot manage to get to here. So occasionally, so the polymer will have a tendency to do that, but it will not always be able to do that in a perfect manner. And sometimes with the matches, there are also mismatches that you have to deal with. Now, it might also be that this polymer says, well, the strength in which the yellow monomers and the oil and the blue monomers and the water interact with each other is not strong enough for me to want to do this, and I may, again, in the case of a weak interaction, simply wander off to infinity, and then you say, well, then about half of my monomers are placed well, and the other half are not placed well, but if the interaction is weak, then the polymer might still try to do that. So there is again here a phenomenon of trying to localize at this interface, because if you do, then you have the option of sort of optimizing the way in which you put your monomers in, but that may not be good enough, and so you may also delocalize. And the question will be, can we describe this model, and can we find where the phase transition occurs as a function of underlying parameters? And I'm going to define a model for this that will describe that. So that is what I'm going to do in the first part. And I'm going to have a look at this phase diagram and tell you a few properties about it. And then in the second half of the talk, I'm going to look at a situation where I am going to replace this flat oil-water interface by something much more complicated. I'm going to think of a water reservoir in which there are oil droplets floating around, and to see how this modifies the situation. And we will actually get to a model that has a percolation flavor, but that will come later. Now, here is the thing that we would like to model. So you have to imagine here this flat interface and this polymer carrying at a microscopic level this yellow-blue disorder, which I didn't put into the picture here, otherwise, well, it would be hard to see. This would be an undirected version of the polymer. So this is the kind of thing that, that you can come across in experiments, and I will mention an experiment soon. This model is too complicated. We're going to have to make the polymer directed, otherwise we cannot deal with it. And I told you yesterday that once you add disorder, things become so complicated that you really have to resort to directed models if you want to make a lot of progress. But the undirected models are there for us to think about as a future challenge. Okay, so as I have already explained, in this model, the polymer, the copolymer in principle, has a tendency to want to stay close to this oil-water interface, because if it doesn't, it will only be able to place half of its monomers in the right medium, and the other half will be mismatched. By going through around the interface, it can try to put more monomers in the right medium, but if it does that, it loses entropy, because there are very few, there are only few paths that stay close to the interface compared to paths that are not restricted to stay close to the interface. So there's again an energy-entropy competition like there is always in equilibrium statistical mechanics, and we are looking again for two phases that we might call localized and delocalized, and we will have to be careful in defining these things properly. Okay, so let's spend 2 minutes on explaining where these things in fact occur. The whole area of copolymers near interfaces is something that is happening in a whole bunch of different applications. For instance, everything in a chemistry setting where you want to build something that prevents stuff to foam, or want stuff to foam, or you want to sort of stabilize certain objects. I will come back to that later when I talk about the oil droplet model. For this, you typically coat objects with such copolymers. So many fats consist of copolymers that have sort of stretches of hydrophobic and hydrophilic monomers that occur in some sort of erratic manner, and therefore fats can be viewed as random copolymers in certain cases. And for instance, here is an experiment that you could do. You could take a copolymer that consists of blocks of ethylene oxide and propylene oxide. So you could, and you can think of these as sort of your two types of monomers. They are actually sort of blocks, but let's think of them as monomers. And what happens is you can put a layer of hexane on top of water. And this layer, well, it's not infinitely thick, but it's rather thick. It would be 10 to the 5th angstrom. And now if you put this copolymer in the hexane, you will see that it starts to, at some temperature, wiggle around this interface. And the width of this thing will be very small. It will be something of 20 angstrom, so much smaller. So you can think of this layer as actually being sort of infinitely large compared to the spread of the polymer. And if you change the temperature, you will see that this phenomenon is not present. So you can actually measure this localization or delocalization phenomenon, and there are various ways you can do that. But for instance, with neutron reflection methods, you can actually see this happening depending on the parameters in your system. Okay, so that is an example of a setting where the behavior of copolymers near interfaces is actually seen in experiment, and you want to understand how these things work. What? This experiment, there's a book by Cosgrove who talks about many of these things, and that book, I think, dates around the late 80s. Yeah. Okay, so now I want to start to model this situation, and we're going to make a little change compared to that situation. Namely, we're going to think of our monomers as being the edges in the path rather than the sides in the path. So that's a small change, but it's not really an important change, but it will be for the model that we do a convenient change. So I want you to now think of a directed polymer, still a path that always goes to the right and up, or to the right and down. But I want you to think of the edges as being hydrophobic and hydrophilic rather than the sides. And a little advantage of doing that is that an edge is either entirely above or entirely below the interface, so we don't have to specify what is happening at the interface. Like here you could say, well, maybe I want to weigh things at the interface differently from away from the interface. So that problem is gone here. And so here you have a picture where you have these hydrophobic monomers and hydrophilic monomers, and in every other way, this model is the same as that model over there. Okay, and we're going to think of these, the order in which this happens, as completely random. This is another idealization of reality, but that is fine. Okay. Now, to set up the model, I need 4 ingredients. So here are the first 2. And, well, as always, we start by saying what paths do we allow. So that is easy. I have already drawn a picture. So our set of allowed paths is all n-step directed paths, well, in dimension 1 plus 1. with steps that are either northeast or southeast. So you can only go up by one and go down by one. It's possible to extend this to more general paths, but I will comment on that later. Then we will need randomness coming in. So omega, which will be a sequence of omega i's, and it starts from n here, is it's an ID plus minus 1 disorder. Okay, and the law of omega is what we denote by this double P. So that's just the product measure. And we say that we picked a case where the plus and the minus 1 occur with equal probability. So for each monomer, you toss a fair coin to decide whether it's hydrophobic or hydrophilic. Again, you can generalize this by looking at different densities, but I will only comment on that later. Let's stick with the simplest version of the model that you have. Okay, so that is simple, all directed paths, and a very simple disorder obtained by tossing a coin. And now comes the Hamiltonian. And the Hamiltonian is something that we have to discuss a bit, because the Hamiltonian is really trying to capture this model. It is minus beta times the sum from I is 1 up to n of omega I plus h times the sign of the ith monomer, so the edge between the ith and I minus first and the ith location. So by this I mean the edge that represents the ith monomer. And so what is happening here? We need to discuss this a bit. Suppose and there are two parameters, beta h, the same parameters that appeared in the model of random pinning yesterday. However, they play a somewhat different role, but I've used the same notation in order to sort of make things look similar. Now, suppose we forget about this h for a moment. And suppose h would be 0, it would not be there. Then, what this thing is doing, it's basically saying, well, if the ith monomer is above the interface, then this is a plus 1. And if it's below the interface, then this would be a minus 1. So this thing here can be plus or minus, depending on whether that monomer is above or below the interface. Now, whether it's above or below interface is important, because that means that it will either see the oil or it will see the water. So the sign of this thing will determine which of the two media you are actually in. And then this omega I is going to be plus 1 or minus 1, and we think of the plus 1 as saying you are hydrophobic, you like the oil. And so if you are above the interface, then this is plus. And if you like the oil, then this is plus. And therefore, the contribution of this would be plus times plus is plus, and you would get a negative energy, which is what you want, because you say, I'm putting a hydrophobic monomer in oil. That's great. It likes that, and so it should get a negative energy reward. No, this is the edge. So think of this as just the edge between the interval between the two things, and that's the edge, and that you should view as the edge that represents my ith monomer, because I'm now having a bond model. Okay? You know, where that just tells you whether you're in the oil or in the water. Okay? Now, if this would be a minus, then it would like to be in the water, and if it's a plus here, it will get a penalty, because then the energy would be plus beta. Okay? So if the H is not there, it's exactly doing what this model is supposed to do. Now, what happens when and the beta is a kind of strength. If beta is large, then the interactions, both the reward and the penalties for matches and mismatches is strong, and you should have a strong, you will have a strong interaction. Now, what are we going to do with this H? This H is a way to bias things and saying, well, it might very well be that one monomer type is interacting with at a different strength than the other monomer type. I mean, if I would leave the H out, then the interaction strength between the two types would be completely symmetric, and there's no need to have that. It could very well be that one type of monomer is having a much weaker interaction with the oil and the water than the other monomer. So this H allows you to bias things. So we can play with this, saying it's a particular way of giving different strengths to the different monomer types, and I'm pulling out an overall factor beta, and with the H I can play. Okay, so that's the idea of this model choice. And then, as before, if you fix the Hamiltonian, you can get your Gibbs measure, as we've seen so many times before, and I'm using here as a reference measure the measure of it's the uniform distribution on all the directed paths. So this would be the law of a polymer chain that is not interacting at all with the interface. So this is just the uniform distribution on my set of 2 to the n directed paths. And here is my normalizing partition sum. Okay, so this is the model that we're going to try and understand. Okay, so 2 different types of monomers, plus or minus 1, hydrophobic, hydrophilic. The sign will tell you whether you're above or below the interface. And this is the energy that monomer I picks up in this random environment. This is an omega, this is a W. So I warn you again that the symbols for the path are different for the symbols for the disorder. They look very close to each other, but I'm sorry for that. Now, there are 2 cases that are a bit special. H is 0 and H is 1. If I take H is 0, then I have already said then both monomers are interacting equally strongly. So it means that the hydrophobic monomers like the oil as much as the hydrophilic monomers like the water. And if I inverse their roles, they hate the other fluid as much as the other. But if I take H is equal to 1, then something is happening here. Then this factor here, which is basically biasing the distribution, would completely kill the minus 1s. So if I take H is equal to 1, the bias is such that it completely kills the hydrophilic monomers. And the case H is 1 would correspond to the situation where the hydrophilic monomers are not interacting at all, neither with the oil, neither with the water, and that I would be in a situation where only the hydrophobic monomers are interacting, liking the oil, not liking the water. And so this is the extreme case of asymmetry. And somewhere in between, you will have a situation where the interaction of the hydrophobic monomers is just stronger than that of the hydrophilic monomers, and that's it. I could also look at the negative values, but by symmetry, that's the same kind of problem. So we're going to restrict ourselves to that regime. So what would we expect? If I would plot beta against h, then I already know that at 1 something is happening. So this is really the interesting regime. Now, if beta is very strong, very large, and h is sort of small, maybe even 0, then there is this, they interact equally strongly, and if I would make the beta very large, it would mean that trying to optimize this would give you a fantastic reward, so you're probably going to localize. So we do expect that somewhere in this region here, you're going to localize. The other extreme case is somewhere up here. If h is equal to 1, then the hydrophilic monomers are not interacting at all. The blues are not doing anything. The only interaction that you see is with the yellow ones, and the yellow ones, therefore the polymer would completely move out into the oil because it would put all its hydrophobic monomers in the oil, and it would be perfectly happy, and it wouldn't pay any price for having the hydrophilic monomers into the oil. So we definitely would expect that somewhere up here we would have a thing that delocalizes, and so the question is, there should be some critical curve in between. And that is what we're going to be working on next. Like for the random pinning model, what is important to understand this copolymer model is that is again how it makes successive excursions away from the interface. Because this Hamiltonian, you can completely understand the moment you would freeze this disorder. If I tell you where it makes its excursions, then I can tell you also whether these excursions are above or below the interface. Once I've frozen this disorder, if I give you all the excursions, you know what the energy is, right? Because an up excursion will correspond to, over this whole excursion, that this is +1, and a down excursion will make this equal to -1, and so I will be adding up my omega i's with a plus or a minus sign with these parameters in here in the excursion. So it's just that in the excursions this becomes all plus or all minus, and therefore if I know something about the omegas in the excursions, I will be able to get my hands on this Hamiltonian. So there is again an excursion way of looking at these things. And so this would put us into business to do the same kind of thing I did yesterday using large deviations of excursions, but I'm not going to do that here. I'm going to have a different way of looking at it. So it would be possible at this point to proceed building up machinery using the large deviation principle for yesterday, but I'm not going to do that. An important difference with the pinning model is that in the pinning model, if you make an excursion, the only thing that you will see is the energy that you pick up at the end of the excursion. Here, once you have fixed an excursion, and this is all +1s, you will start to see much more because you see a sum of all the disorder variables in the excursion. So this model is considerably more difficult than the random pinning model because the way the disorder comes in is much more sensitive than for the pinning model. Okay, so what am I going to do next? I'm going to define for you the free energy, and I will define for you what the localized and the delocalized phase are exactly about. And then I'm going to derive some qualitative properties of the phase transition curve. So let's begin with the free energy. Well, the free energy is defined as always. You take your normalizing partition sum and you want to know what its exponential growth rate is. And standard subadditivity arguments of the type that were already discussed in the first tutorial do allow you for this model very easily to prove that this free energy exists and that it is almost surely constant with respect to the disorder. So you freeze the disorder, and for typical disorder, this free energy doesn't depend on the disorder. That's this self-averaging property, but it does, of course, depend on the law according to which you've chosen your disorder. Yeah.
For the non-randomness of the free energy,
Subadditivity argument means that you have to use the subadditive ergodic theorem. Yeah, so it's subadditivity for a random process, not numbers, right? So this is just Kingman's subadditive ergodic theorem. Okay, so this thing exists. Now I'm going to show to you that this thing has a lower bound. There's a quenched missing here, I'm sorry. So that should be here as well. Now, before, for the random pinning model, we said it's very easy to see that the free energy can never be negative. It is always non-negative, and then localized was defined as it's strictly positive, and delocalized was defined as 0. Here, the lower bound is not 0, but something else, namely the product of our two parameters, beta times h. And I want to spend very briefly explaining why that's the case. The argument is very similar to what we did for the pinning model, but there's one ingredient coming in, namely a law of large numbers for the disorder. So let's see how that works. So as I've done before, I can think of Si as the realization under the path measure of the ith, the position of my ith monomer. So if I abbreviate this sign thing that tells me is my monomer bond above or below the interval by a delta I, then this partition sum for finite n and fixed omega would be this expectation, where this just abbreviates the sign that is in here. The minus sign disappears because the minus sign is also in the exponent of the Gibbs measure, and I'm supposed to take the expectation over over the law of the non-interacting random path. So this is just the path that gives equal probability to all of the 2 to the n directed paths. So this is our object, and then what we do to get a lower bound, we stick in an indicator as we did before, by saying you never go below the interface. So I can stick this in for free. So this says you will never put your any monomer below the interface. You will stay up the interface. The moment you do that, this thing is 1 and it disappears. Okay. And so this factor is now no longer depending on the path. It only depends on omega, and it comes out in front because this is an expectation only with respect to the path. So this factor comes in front. And what you're left with is the probability that under the non-interacting polymer, you would not cross the interface. And then, now this factor is harmless. This is a polynomial decay. This decays like n to the minus 3/2, so it can go into the exponent at a logarithm factor. And here, something nice is happening because the omega i's were fair coin tosses, this sum does not grow like n, but like little of n. So I am not seeing this. It doesn't contribute to the exponential growth rate, and what I'm left with is beta h times n. So as a lower bound, I find something very simple, two terms that are not linear in the exponent, and I'm just getting this term here, and that is exactly why the free energy, the quenched free energy is larger than beta times h. Okay. And this beta times h is apparently what's coming up when I'm having a delocalized strategy. And therefore, let's define the difference between the free energy and its lower bound. So we're going to define G of quenched of beta h as the free energy minus its lower bound. And we're going to call this excess free energy. And now this is a thing that is bounded below by 0. And it makes sense, therefore, to introduce two phases, a localized phase where it's really larger than 0, and a delocalized phase where it is 0. And the fact that we want to call this delocalized is reasonable because the lower bound here exactly came from a strategy where I'm not intersecting the interface at all. And therefore, if I do intersect the interface, I will probably or hopefully be able to get a higher free energy. So this is very similar, but slightly different than what we did for the pinned polymer. Okay, so our task then is to, now that we have defined these things, to say, well, what part of the parameter space, and it's this strip really that we're interested in, what part of this strip is the localized phase and what part of this strip is the delocalized phase. And here is how we are going to do that. We can define the critical curve as the point where you change from a 0 value to a strictly positive value. So the separation between these two phases will be our critical curve. And from that picture over here, we already expect that it should somehow look like this. And in fact, using convexity properties of the free energy, you can prove that this curve is a unique separation of the two-phase diagram. So if you, for instance, if you move in this direction or in that direction, you will only see it once. And you can prove that beta times h critical beta is actually a convex function. So these are all very general things that come out of convexity properties of the free energy. I'm not going to bother you with that. And you can also prove that the curve is really starting at 0 and it's somewhere having an asymptote equal to 1 up here. So these are qualitative properties that you get out with a little bit of work. Apparently, if the symmetry, if you're in a completely symmetric situation, then already a tiny interaction will allow you to localize. This is sort of very similar to what we saw with the pinning model that was also having a curve that sort of got up at 0. And here, this is the limit. You know, if you have a huge interaction, then in order not to localize, you really must basically kill the interaction of one of the monomers, and therefore your curve is moving to 0. So it is a picture that looks like this. So maybe I make it somewhat bigger now so that you can read this better. Beta h, and here's 1, and there's a nice curve that separates the localized from the delocalized phase. So that is what the picture looks like qualitatively. And okay, now the next thing that I'm going to try and do is to try and get our hands a bit on the qualitative properties of this curve. So I would in principle have the option now to try and bring in this whole big variational machinery that I applied yesterday, but that's in this model somewhat heavy and somewhat complicated. I'm working with Erwin Bolthausen on trying to do that, but I'm not going to take that route here. We're going to take a somewhat more moderate route, and I'm going to give you 3 theorems, one that gives an upper bound for this curve, one that gives a lower bound for this curve, and one that is telling us something about what is happening down here. So the first theorem is an upper bound. It says this critical curve is upper bounded by a very simple curve that is written down here. And this curve sort of looks like this. Okay. And this will come out from an annealed estimate. In fact, if I would introduce the annealed version of the model, then this curve would exactly be the critical curve of the annealed model. And if I would have to do a variational analysis, I would have to look at that thing in some more detail, but it is an explicit object. I want to give you a proof of how you do that. So let's look at this excess free energy, which is the free energy minus h. And I'm sorry for missing the quenched upper index here. I should have added that. Now, the free energy, if there would not be this minus 1, then this thing here would just be the definition of the free energy. You take the expectation of your minus your Hamiltonian. The Gibbs factor, you take the logarithm of that, and the expectation, as long as it's in front of the logarithm, can be handled because of the law of large numbers, because of the self-averaging property that for every fixed omega you get the same exponential growth rate. The fact that I have to pull out a minus 1 here is because I was compensating my free energy with a factor beta h, because it was always above beta h. And this you can do by putting in the minus 1 here, because the minus 1 just means you pick up this sum here, which has a part beta h times n, but it also has a part beta times this sum. But this sum, by the law of large numbers, is not growing linearly, so this cannot affect the exponential growth rate. So the effect of going from f to g is just by sticking a minus 1 in here. Okay. Now I make my annealed estimate. So I interchange the log in the expectation. So this is this really, here you lose something substantial because you go from quenched to annealed, and this is typically not an equality. And now once you have pulled this expectation here, you can interchange it, and now you can just first take the expectation over the disorder at a fixed path. So if the path is fixed, all the delta i's are fixed, and you can just take the expectation over omega I, and that's easy because the omega I just take the values plus and minus 1 with a half. So if you carry out this inner expectation, you will simply find a half times this factor here and a half times that factor, as long as the omega I is not plus 1, because then this would be entirely killed. Only for the minus 1s, you pick up something, and then that's why this would then be minus 2, and that's why there is a minus 2 in front of here. And so you just do a simple calculation, and you see that you get a simple factor where just this indicator of being below the interface at your ith monomer is up here. And if this whole thing here, this factor, is smaller than 0, then this whole expectation will be smaller than 1, and therefore the expectation will be smaller than 1, and therefore G will be smaller than 0, smaller than or equal to 0. We already know that it's equal to 0. We already know that it cannot be negative, so it will be 0 as soon as this factor is smaller than or equal to 1. And that occurs when this happens, except that I had a typo here. This inequality should be the other way around. So if h is above this curve, I will have an estimate for this thing where this is smaller than or equal to 0. It cannot be negative, so it will be 0, and therefore I will be in my delocalized regime. So it says if my h is above that simple curve, the dotted curve is exactly this curve here, I am delocalized. Okay, so that's a nice estimate, very simple. Now there's also a lower bound that looks very similar, except the 2 beta is replaced by 4/3 beta, and this curve looks like this. This was proved by Thierry Baudineau and Giambattista Giacomin in 2004. And this bound is based on coming up with a possible way in which your polymer might localize, and then using that way to give a lower bound for your free energy. And it's basically building on the idea that the copolymer looks at the disorder that it has built in itself, and it says if there are some stretches where there are very many hydrophilic monomers, then what I will do is to try and put those stretches of hydrophilic monomers below the interface, and I will not care about doing anything more fancy. So this is one way for the polymer to localize, is saying if there are enough blue stretches coming up, I will dive below the interface, and if the stretches are not long enough, I will simply ignore that, and you can, by playing with that, get a lower bound. And it will be the content of the tutorial this afternoon to give the proof of this lower bound. So to go into this business here, saying there is a way that you can localize, and this uses a little bit of basic large deviation theory, nothing fancy, but in this model you have to put things cleverly in the right place to get the thing working. So we have now a situation of the picture that I've drawn here. Here is our curve. We do not know the fine details of this curve. No expression known for it, even though you can derive a variational expression for it, but I will not discuss that. And we have 2 explicit and rather simple upper and lower bounds for this thing that seem to catch the qualitative structure of this thing. Okay, what am I going to do next? I'm going to tell you something that is happening close to the origin. And this is the following result. The behavior of this curve for very small beta is linear in beta. And it's linear with a certain constant Kc, of which we know that it's positive and finite. And the way this is proved is that as the interaction gets very weak, this polymer has a tendency of moving away further and further from the interface. If it hits the interface, it doesn't get such a wonderful reward. So it's probably going to make long excursions and only occasionally sort of hit the interface at spots where there are a lot of blue ones or a lot of yellow ones next to each other. And so if you want to prove a thing like this, you would hope that you could do it by some kind of Brownian scaling. You say, in the weak interaction limit, I'm going to make very long excursions. If I'm localized well, I'm still going to make long excursions, so I may hope that these excursions are Brownian-like, and that the disorder along these excursions is also going to be Brownian-like. So maybe there is some kind of Brownian model that would capture this. And indeed there is, and so I will put that on the following slide. And the fact that there is this sort of Brownian scaling is also transmitting the message that this limiting result is not just one particular result, it's actually something that has a high universal flavor. In fact, there is so both Francesco and Nicolas in their thesis, the PhD work, have sort of looked at this thing in much greater detail, and Francesco and Giambattista Giacomin are expanding on this in more recent work, that there's a whole class of similar models that seem to have this same kind of scaling behavior. So there's something very universal behind this object. And so let me give you a very quick statement about what this Brownian model is that you would have here. It turns out that the free energy of our model, when you fix a beta and fix an h and you put an epsilon in front of it and you make the epsilon very small, that this free energy is scaling to a limiting free energy. And this limiting free energy is basically the free energy of a Brownian copolymer with Brownian disorder. And the way you would build this thing is that you would take a Brownian motion here that would play the role of disorder. I forgot a little b here indicating the whole path. So this would be a kind of disorder which no longer is plus or minus 1 saying whether a monomer is hydrophobic or hydrophilic, but it describes Brownian increments, and so it would correspond to a kind of continuous copolymer where for every piece you could say what is its hydrophobicity. So how hydrophobic is it? Or how hydrophilic is it? So a piece would not be assigned a plus or minus 1, but some real number, and this real number would describe how hydrophobic or how hydrophilic it is. And then you can look at the set of all Brownian paths rather than directed Brownian paths, rather than just going up with plus or minus 1. Your path would be living in Wiener space, and you could define a continuum Hamiltonian that would be sort of a continuous analog. Here you have the sign of your Brownian motion. Here you have the disorder that replaces the omega I. Here you have your bias that replaces the h. You have an overall factor beta. And now, this is actually a stochastic integral, but this makes perfect sense. And you could define a kind of Brownian version of this. And in fact, the proof of this weak interaction limit here uses that model. And it uses a way to compare but so you would still freeze the Brownian disorder, and you would define this as the quenched free energy with respect to the fixed Brownian disorder, and you would only take the expectation over B. So you wouldn't change anything. You would keep the order. Yeah. And you can do a quenched and annealed version of that as well. Okay. And the proof of this is basically using a kind of coarse graining argument, because the path is up in the exponential. I mean, all these weight factors are exponential. So this doesn't come out of a standard invariance principle. You have to do all sorts of estimates to make this work. But I want to emphasize that this is a very general things. So there are different models that seem to have the same behavior. So I can fiddle around with my Hamiltonian a bit, and I would still end up having this result. It's quite robust. Now this number kc, so this is the slope of this curve here, has been debated a lot. The upper and the lower bounds on the curve will show that this number is somewhere between 2/3 and 1, because the upper bound has slope 1 and the lower bound has slope 2/3. So it must be somewhere in between. And in the physics literature, there were people arguing in favor for the 2/3, and there were people arguing in favor for the 1. And this went on for a while, until finally it was proved that it really is not 2/3 and it's not 1. It is really, so this came out of numerical calculations, doing sort of clever estimates, that it's a number that is somewhere like 0.83. And it was proven 2 years ago by Fabio Toninelli that it is really smaller than 1. And for some subcases, it has actually been proved that it is also strictly larger than 2/3. But we don't, mathematically, we don't have any much information other than these two bounds. And the proofs are a bit tricky. Another interesting, tantalizing thing that came out of the numerics is that the same number kc, if I use that number in this function here, as an upper bound we had here 2 beta, and as a lower bound we had 4/3 beta. If you would plug in the kc and would look at what this curve looks like, it seems that for, well, beta values that are not too large, the actual critical curve seems to be fairly well approximated by this curve. So this, in some sense, this gives an even more important value to the role of kc. And for some time it was actually, the question was there, is this an equality? And it is not an equality. So it has been proven that the true curve is not of this shape. Okay. The proof that we gave, so that I gave with Erwin, was just there exists a kc. And without, no. Oh, no. No, you don't see the K. Yeah, you see the Kc emerging in this sense, that the Brownian polymer has a critical line that is linear. It has the slope Kc, but you can't tell what this Kc is. So the Brownian motion approach will only just give you the existence of the thing and not what the value is. And it's open what the value is. We would like to know. Okay, I'm going to flash a couple of more theorems at you, 2 theorems, or 3 theorems to say what more can be done. I won't spend too much time on this. You can prove some path properties that are very typical for localized and delocalized behavior. So in the localized phase, we know, of course, that you will intersect the path at a positive density, because you see this from the fact that the free energy does not have a 0 derivative. And again, the length and the height of the largest excursion up to time n is of the order log n. We know that in the delocalized phase, well, if you are away from the critical line, that you intersect with 0 density. We definitely believe that you will only intersect finitely often, but we do not know how to prove that. And in fact, what is known is that you do not intersect more than log n, and the prediction is that it's order 1. You have to be a little bit careful here because this is probably only true in what would be called the average quenched measure. So it has been shown that if you freeze a particular environment, then you can find you can find a subsequence of n along which this number could sort of exceed any finite number. But apart from those technical details, basically the message is in the delocalized phase, you should at some point leave the interface and never come back. So not everything has been settled about this yet. Then it was shown that the phase transition is at least second order. So if you come from below, for instance in this direction, here the excess free energy is positive, here it's 0, then as you approach the line it will go to 0 at least as fast as a quadratic, and this is given by this estimate here. So the phase transition is at least second order. It is still open to prove or to decide whether the order of the phase transition is order 2 or is actually higher order. So whether it would approach the curve faster than quadratic. And we seem to be moving towards a prediction that it would actually go a bit faster than quadratic. But nobody really knows. So some people believe that it is higher than second order. Then it has been proved that in the localized phase, the free energy is infinitely differentiable. So that will tell us that nowhere in this phase is there some other curve that we hadn't noticed. Certainly not a curve where things are, things could be non-analytic, but they will still be infinitely differentiable. I do not believe that we should expect that things will be analytic in this regime because there is something called Griffith's singularities. I will not say anything about that, but there could be very weird stretches in your disorder that would mess up the analyticity and not mess up the infinite differentiability. But that's a statement for experts. There are many ways in which you can extend this thing. You could replace the disorder by something more general. I already talked for the Brownian model about saying you could give a real value of the disorder, so you could talk about a degree of hydrophobicity and hydrophilicity. You could have monomers that could have different types of strengths of interacting, possibly in a continuum manner. You could allow your paths to be more general than paths that can only jump to northeast and southeast. Can all be done, and it doesn't really change much of the picture. Only the fine details will become different. And it has been also proven that these upper and lower bounds are not, they are also really strict. And one of the targets that I'm trying to do with in a paper with Erwin Bolthausen that is in progress is to apply this variational approach I was discussing yesterday to this problem and see whether we can make progress there.
So it shows that since these two curves, the angle and French divergence, you
Yeah.
get zero.
Yeah.
Which means your relative entropy,
Yeah.
yesterday is always
Yeah.
not zero. Right?
Exactly. Right.
You have the same formalism with work.
Yeah. So indeed, we have variational formulas for these things for both of these curves. These variational formulas are a bit more complicated, and so there's already for the pinning model, it was a struggle because you have all these relative entropies and you know, projections of words on letter sequence. And now the functionals that come up in the variational problem are even a bit harder. But yeah, everything is still, so the same formalism works. We're busy trying to work out the fine details of that. Okay. I now want to come to part 2 of the talk. So in the remaining 25 minutes, I'm going to talk about an interesting variation on the same problem where the interface is not flat, but actually has a kind of random structure. And a flat interface is also something that is really an idealization, because this thing will start to fluctuate, and it's very hard to keep something flat like that. So now, the thing that we would like to model, which we are not capable of doing, is a model where you say, well, I have a big water reservoir and there's droplets of oil floating around. So think of this as a kind of emulsion. And we have this copolymer lying around. On the copolymer, there's still this disorder of the hydrophobic and hydrophilic monomers, which I'm not drawing in here because then there will be too much blue and too much yellow around. But imagine that this thing is again a concatenation of yellow and blue monomers that have a tendency to want to be in the right medium. And so this is the kind of thing that we would like to model, but it is too difficult for us. And it's too difficult for us for two reasons. First of all, a polymer chain like this would not be directed, and we have trouble dealing with that. But also, this medium here is also too complicated. We have to give the way in which the oil and the water are living, we have to give this some kind of structure. So that's what we're going to do. We're going to build a somewhat different model from this. Now, you have to realize that once you start to work on a thing like this, there is yet a third level of disorder coming in. There is a disorder in the way the path is configured. This is given by this Gibbs measure. There's disorder of yellow and blue monomers along the chain. And if I get this thing here, if I view it as a kind of medium in which I'm saying, there's a third level of disorder coming in because of the medium. So we have to deal with 3 types of disorder, but that's not much harder than to deal with 2 types of disorder, is it? Or is it? Good. Okay. We again expect that there will be some kind of phase transition between a localized and a delocalized phase. A localized phase should be something where you say, okay, I'm spending a lot of time near the boundary of these droplets, because if I'm near the boundary of a droplet, I can try and put as many monomers in the preferred medium, and if I'm away from them, I cannot do that. And in that phase, I would expect that I would sort of wiggle around the boundary of the droplets, and then when I have to leave a droplet, I will sort of pretty rapidly go over to another droplet and try to spend a lot of time near the boundary of that droplet. And on the contrary, if I would be in the delocalized phase, I would say, well, what the hell, I don't care much about the interface. I'm just moving through this medium as if I don't see the droplets. So localized and delocalized should mean something different here. And we will try to get our hands on that. And we will see that in the model that we build, this whole localized versus delocalized business becomes much more complicated than in the linear interface model. And I will show pictures of that which have really sort of surprised us. So we're thinking here of a model of a copolymer in an emulsion. Make me think of it as a microemulsion of having many small droplets floating in water. And things like that are actually coming up in a very everyday example, namely milk. Milk consists of fat droplets that float around in water. Well, milk contains many other more things, but those are two ingredients. And if we would just have that, you would put your milk jar in the fridge, and the next morning you would take it out and you would see that all the fat is sort of, all the droplets are somehow separated from the water. And you would have to shake your bottle before you start drinking it. So what is happening in the factory that produces the milk? They add something to the milk, which is a copolymer called casein. And this copolymer will wrap itself around the fat droplets. And so these fat droplets will have this copolymer stick to it, and it's wobbling its tail. And because it's wobbling its tail, the fat droplets cannot meet each other, and they cannot coagulate. And this has an interesting name. So this is used to stabilize milk. So this kind of model is something that has something to say about that particular problem. Of course, I'm being the usual mathematician here, being proud of some nice application, whereas the reality is, of course, infinitely more complicated than what we're having here. But still, I mean, this is really what is happening. Okay, so the model, this model here is too difficult to deal with. So what are we going to do? We're going to build a model that is supposed to be easier. And I will draw a picture on the next slide, but let me tell you what it is that we're going to do. We're going to simplify life in order to be able to describe this. The first thing is there is z squared, and I'm going to chop it up into large blocks of a size that may depend on the length of the polymer. The polymer has a certain scale, and I can decide on a scale of chop up my thing into blocks. Then what I'm going to do is the copolymer is going to be something that is still a directed path. I'm going to take a directed path that can not only go northeast and north-south, but it actually can go up, down, and to the right. So this was the kind of paths, it's called ballot paths, that so they look like this. So it's a directed self-avoiding walk. Those are the paths that I will allow. Okay, and I'm chopping up my space into big blocks. Where this has length ln. And I want the path to be doing this kind of behavior, but I want it to only be able to go out at either this corner or that corner. So I'm putting in a very severe geometric constraint on my set of paths, is that I say you enter at a corner, and then you will do this type of path in this block, but you cannot leave the block anywhere else other than here and there. So this is a completely unphysical constraint, but we do it to allow us to be able to do mathematics on this problem. Then again, every monomer, as before, will have a probability half to be hydrophobic and probability half to be hydrophilic. So along this curve, you will see the blue and the yellow monomers appearing again as before. And now comes the additional randomness that comes from the emulsion. We decide to make every block here independently completely oil or completely water with a certain probability p, just as if we were doing percolation. So here is this chain with the blue and the yellow ones. We know that the path has to lie in a certain class that has a severe corner restriction. And then we're going to make these blocks independently entirely oil or entirely water with a probability P. And the randomness that you get for your oil-water interface is labeled by another omega. We call it capital omega. So this is the randomness of my oil-water block. So this is the randomness of the emulsion. And then what we're going to do is we're going to make the interaction Hamiltonian a little bit simpler. Namely, we're going to say, okay, a yellow monomer in a yellow block gets energy minus alpha. A blue monomer in a blue box gets energy minus beta. And let's forget about what happens when a blue monomer is in a yellow box or a yellow monomer is a blue box. Let's not give that any penalty. So there are only rewards in this model, no penalties. Doesn't really change the problem a lot. In fact, you can map this model into a model where you would have the penalties also, but let's not worry about that. So we have a model that looks like this. I have a random organization of blocks. These blocks are large. They have size Ln. Ln will be a large number depending on the length of the polymer. There's a percolation structure of these blocks. And then I have a path that carries the blue and the yellow monomers along its trail. I haven't plotted that because there would be too much blue and yellow in the picture, but it's there. And I allow all possible paths with this funny restriction that once you enter something here, this pair of blocks, you can only leave here or there. Okay. And so there are three types of randomness: the path, the disorder along the path, which I haven't drawn, and the disorder of the emulsion. And this is the model that we want to look at. Okay, and this is a model that we looked at in detail, and I will show you that we found an absolutely remarkable phase diagram behavior, which is much more complicated than you would naively expect. So there are a couple of parameters. There's the parameter of the density of the oil blocks. There's these parameters here that talk about the two rewards. Without loss of generality, we may assume this, saying the interaction with the oil is stronger than the interaction with the water. Yes? Yes, that is what one would write. I mean, if the polymer is in a block like here that has an interface, then it will probably want to wiggle around this interface because if the parameters are such that they want to localize. So the polymer is still want to sort of localize around the interfaces. Oh no, that is just a geometric constraint. I would like this path to be everywhere, but we put in this geometric constraint that you can only leave a block at, when you enter a pair of blocks, you can only leave it here or there, just to be able to do mathematics. It's a completely unphysical restriction. Here I am. I will not leave this block until I decided to leave it there. Then I'm in this pair of block. I wiggle around and I decide to go out there. So this and here I am in this pair of block. Could do anything. I decided to go out there. Pairs of blocks. Yeah. And the reason why we're doing this is that we can then sort of use percolation arguments to deal with this. And we need a coarse graining limit where we're going to make the blocks large, but they're still going to be small compared to the length of the polymer. And this is an important way of taking a limit because it means that I am separating the polymer scale and the emulsion scale. The blocks are very much smaller than the polymer, and but the blocks are still very large. So in each time the copolymer is in a block, it can sort of self-average in that particular block. And then there is also some self-averaging going on the polymer scale, which needs percolation theory. Okay, I'm going to show you two theorems and a bunch of pictures, and then we will be done. The first theorem says the free energy in this model, which has three types of randomness, exists. It's non-random, almost surely with respect to the disorder along the polymer and the disorder of the emulsion. This does not follow from a sub-additivity argument. That does not work because of this discrete block structure. You have to use concentration of measure estimates, and these were also discussed in the first tutorial. And what happens is that I can write down some complicated variational formula for the free energy that contains a number of ingredients. The polymer can, when it enters a corner, it sees a pair of blocks in front of it. And there are four types: oil, 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 water, water, oil, and water, water. And it's going to spend some time in this pair of blocks. And I can prove a free energy limit in each of these four blocks. Then I can try and keep track of how often the polymer, when it goes through this percolation medium, visits these four types of blocks. That's a percolation question. And there is some ergodic theory going on this emulsion scale using percolation arguments. In fact, it uses oriented percolation. And then I have to keep track of how often, what fractions of times I am actually spending in these four types of blocks. And there is a big variational formula that is a supremum over all sorts of things. And that, okay, and then what we do is we are going to analyze this variational formula in detail. We're going to analyze its ingredients. We're going to analyze how all these ingredients are put together. And out comes behavior that allows us to say something about the phase diagram. And what is very important is that there are two different regimes which are reflecting the effect of the emulsion and basically are reflecting a percolation kind of behavior. If the P is large enough, then the oil blocks are have such a high density that they start to percolate. So that I will be seeing in my medium basically a big infinite cluster of oil droplets. Whereas if the density is too small, the oil blocks do not percolate. And I can make the P even smaller so that the water blocks start to percolate, but I'm going to just look at P larger than a half. But by symmetry, we can always swap things around. So there will be it turns out that there's a difference between whether the oil blocks percolate or not. And why are we focusing on the oil? That's because I restricted my parameters alpha, beta such that the oil is the preferable medium. The copolymer likes the oil more than the water. If I would turn that around, everything would be the same, but we choose that particular direction. And it turns out that in these two cases you have, in the supercritical case, you have 4 phases. And in the subcritical case, in the supercritical case, you have 2 phases. In the subcritical case, you have 4 phases. And let me show you what these pictures look like.
This is just percolation, no orientation.
Percolation, only percolation. So the P here is coming from, it's basically the critical value for oriented percolation on the quadrant. Oriented, because I'm having directed paths. Yeah. So the phase diagram in the supercritical regime looks like this. This is the reward for the oil monomers and the hydrophobic monomers, and this for the hydrophilic monomers. And there's a certain critical curve that actually touches the 45 degrees line. I don't have time to tell you why that is happening, but it has, again, a single critical curve separated by a delocalized and a localized regime. Yes, yes, you can flip things around, but exactly. And the two phases are characterized by this kind of path behavior. So this is the supercritical phase where there is some sort of infinite oil cluster. And in the localized phase, the copolymer tries to wiggle around the boundary of this infinite cluster. So it likes to be able to stay close to the interface and put as many of the yellow and the blue monomers in the right medium. So this is a version of localizing around the boundary of the cluster. And in the delocalized case, the interaction is not strong enough and say, well, what the hell, I'll just, I don't care about this interface. I love the oil, and I will just move deep into the infinite cluster of the oil, and I don't care to follow its boundary. In the subcritical case, there are three critical curves, and they have a pretty complicated structure. There are two delocalized phases and two localized phases. We know something about these curves here. We know very little about this curve. We haven't even proven really that it exists, but it's pretty obvious that it should be there. And there are some question remarks about this phase diagram, but this definitely is what it is. And I remember when we were working on this with Stu Whittington, sort of every day we had another guess. So Stu said, isn't that interesting? We have a time-dependent phase diagram. And in fact, we had completely missed this curve. And when I started to work on this with Nicolas, Nicolas found this extra curve and said, well, there's even more going on. So it's a phase diagram that took us a long time to even sort of guess what it was. And in these four phases, you have very strange behavior. I'm almost done. You have two delocalized and two localized phases. And this is a phase where you say, I don't care about any form of delocalization. I just go as I please, and I will hit blue and yellow in some sort of way. This phase is where you are still spending most of your time in the blue and the yellow and not spending really much time in the near the boundary, but you will somehow have a greater tendency of hitting small droplets. You will target them, but you will not really spend time close to the boundary. This is quite remarkable. In the two localized phases, you will have a tendency to stay close to the boundary if you can. And in this phase, you will mostly do this at the outside of your droplets, whereas in this phase, you will even be willing to sort of target little water holes in your droplets and even pick up the interface there. And all these four cases seem to be possible. So it's quite a complicated behavior, which, well, it surprised us, and we certainly did not expect this at all. And it took us a long time to, yeah, we have a proof. In this phase diagram, there's still a couple of things, but this we have, this qualitative behavior we have really proved. Yeah, how do you do that? Well, it's because we look at, it comes out of this variational formula that has all the ingredients of how you visit blocks, and you get control over you know, how often you hit interfaces in pairs of blocks that have water and oil. So, so this is my last slide. It's really quite remarkable that this copolymer motion model is so rich. And now, we had this very funny corner restriction saying you can only leave blocks at corners. This is a completely unphysical, but it was a key thing to be able to set up a nice variational mechanism. And Nicolas and I are currently trying to get rid of that. say, well, don't put in this corner restriction. And it seems that this complicated phase diagram is just going to survive. This is not something that is a byproduct of this corner restriction. It was very important to do this coarse graining limit where you say the blocks are large but very much smaller than the length of the polymer, because this allowed you to separate the polymer and the emulsion scale. And so it's a model with a microscopic disorder and a mesoscopic disorder, and the separation is very important. Tomorrow I will be describing a model where I have also disorder, but they are both microscopic. And then you don't have the separation of different scales, and therefore you couldn't do anything of this type. So that is what I will talk about today, and I think perhaps this should be your take-home message, that it's really remarkable how complicated this model with the droplets could be, but it's also a lot of fun. Thank you very much. Not of the copolymer type. I don't know. So,
You're the pictures of what the four phases mean.
yeah.
So are there physical systems which are known to have such?
I don't think there are experiments that would sort of really see these four phases in the subcritical regime. In the supercritical regime, this is pretty obvious because the boundary of this cluster is like an infinite. But I don't know. I mean, there are certain experiments certainly where you see part of these phases that it sort of wiggles around the droplet. But there would, for instance, I think you will see the distinction between the two delocalized and the two localized. That has been seen. But the sub-distinction between these two, and these things are meeting at two tricritical points, which is another sort of totally crazy thing.
Can you tell something about the two localized phases?
Yeah, so it means there's a range where you have alpha, some not too small value, and then you make beta from moderate to large. And so that is where the distinction is here. So in this phase, I will only target the outside of the droplets, and here I will start to target both the inside and the outside because the reward is good enough to do that. Yeah, L2 corresponds to this one here. Yeah, the script, this should be a script. So the L2 is this phase and the L1 is that phase. Yes? Yes? Yeah, in fact, I agree with that. So, yeah, because there's a whole, if I would draw this everywhere else, there are all sorts of curves going on here in the symmetry again. But you have to be careful that once you flip alpha and beta, you need to go from p to 1 minus p sometimes. So you have to be careful. But indeed, you can just put this whole diagram in the plane, and there's much more. So it's tricritical in the quadrant.